Welcome. We're in chapter 3 of Kuchemann, and now get to do propulsion, which is great. So we're going to walk through a couple equations. It's actually really fascinating to watch a lot of these propulsion things kind of collapse together. So this one will be kind of equation heavy, and I'll come back in the next one and show you some graphs and stuff. That's pretty awesome. So from a propulsion point of view, we want to think about air coming into something that isn't going to make sense, but I want to make sure we're treating it right theoretically. So you have some free stream velocity coming in, and you're at some altitude, so there's a density there, there's a temperature there, there's a pressure there, and you've got some sort of area, and there's a jet velocity coming out the back, and thrust is effectively then just the mass flow rate and the difference between the jet and what's coming out. Okay, from a control volume point of view, that's why I draw this little weird, like, we're going to think about things like how does the air, this would have extra drag because it's shoving the air out and blocking it, and so we will eventually kind of track down a lot of these effects, and again, pretty interesting to see what you can do. I guess again with just kind of these high level assumptions. But that's really the main one. And then again, if I write this down, that's rho 1 or rho 0, and then V0, A0, V jet minus V0. Okay. And first thing is just we want to say that the entropy is conserved. So that's kind of mass is conserved. That's why I was able to split the m dot out. From an energy point of view, we have that whatever the enthalpy is plus 1/2 V0. So kind of enthalpy plus the kinetic energy squared. And then whatever the distance is, H1 plus half V0 squared is going to be, the difference between the two is kind of the heat minus the work. Now, in this situation, if we were doing work on it, it would be, us turning a fan or something like that. And, you'd have to account for that. Mostly what we're going to think through is more like just, because we're talking high speed, we'll really think through more like a ramjet kind of situation where, we're not doing any work to the flow. We are going to add heat to the flow, and we'll add heat from kind of shockwave compressions. And then, we walk through, if you saw some of the derivations, we went and talked about entropy, things like that. And so you have a couple different ways you can think about I'll write down a few formulas. So isobaric, right? Remember, it just as a reminder, any isobaric process, you'd have that a very simple relationship between density and temperature. You can have an isothermal, right? And then you'd have, P1 over P2 is equal to rho 2 over rho 1. And then isentropic, and we walked through that last time, where you have sort of P over rho raised to the gamma is constant. Okay, and remember in a situation Bernoulli can apply where we have no work, and so I'll write here not to cover up my. Well, actually keep it down here. So remember that gamma over gamma minus 1 times P1 over rho 1 plus 1/2 V1 squared. Remember that's kind of constant. Well, and if we're going to add energy, you would add energy and change that constant. All right, so the thermodynamic process, then I'll draw here, not going to cover up myself, and really this is a temperature entropy diagram, and so state 1, the 0 to 1, heat addition 2, and then this is state 3, but we're actually going to call that the jet. It's kind of the end state. Now, in this heat addition process, this is where heat's coming in. Really, we are concerned here with this would be some sort of maximum temperature limit. So we're going to talk about that. That's going to set up a lot of the differences. And just from a conservation of energy point of view, you have really that the difference in kinetic energy V source squared is going to be just, Cp, there's a negative there, T jet minus T2. right? That whatever I'm able to convert there, right? It's coming from that heat addition, and we can actually go through and solve for, hey, what's the relationship of the jet compared to the free stream from this equation? And so I'll write that down. 1 plus, 2 over gamma minus 1 Mach squared. And there's a few steps from here to here. It's all kind of the ideal gas relationships, some of the, pulling the gammas, converting velocities into Mach numbers, things like that. So you can walk through the process. It's not too bad. It can take a few sheets of paper. And we see sort of this form, T jet minus T0 minus 1, 1/2. Okay, so far this looks a little messy, but let's just see if it's got the right terms in it. So we know as we add heat, it should increase the jet. Okay, that makes sense. And then depending on the ratio of the temperature to temperature not, kind of decrement on that. Yeah, okay, so this is making sense. And we can go in and actually see, we know that T jet over T0, we actually know that's jet over 0 is the same thing as 2 over 1, right? Or they would say that T1 over T0 is equal to T2 over T jet. Kind of that ratio is the same because this is at least for constant pressure combustion, and we might come back and change that. But this is happening at P1, which is equal to P2, and this is happening at P0, which is equal to P jet. It is assuming that the jet's fully expanded, but we end up, because of that, we end up having the ratio of those two temperatures are the same, and that's basically just a kind of the thermodynamic cycle. And so because of that, we can write this down as 1 plus that heat addition divided by CP T naught, and then 1 plus gamma minus 1 over 2 Mach 1 squared over 1 plus gamma minus 1 over 2 Mach 0 squared. Right? And really we're going to see this one a lot. This is actually, this whole term here, this whole thing is really just the ratio of those temperatures. Like this is the ratio of, T1 to, it's actually, it's written as ratio of T0 to T1. And it's basically coming from the compression, right? The Mach compression of the cone. So that's pretty useful, okay? But the full efficiency of this whole process, right? If we want to go back and say, what are we really trying to look at? We're trying to take a look at what's the thrust energy, and how is that comparing it to the energy that we put in. So if we had to say that the propulsion efficiency, right? It is so divided by that Q, and it's kind of the thrust times velocity, right? But it's going to have two terms, right? And it's going to have a sort of a thermal portion, and it's going to have a kinetic energy portion. And so this whole thing, we usually will split up and say it's N jet and N thermal. And so the N jet is actually taking a look at V0 Vj minus V0 and comparing that to the change in kinetic energy. Okay? And then our thermal one is going to take a look at the change in kinetic energy compared to what we put in. Okay, and so I'm going to play with this one first, and this you can go work through and see that it is just T jet minus T0 over T2 minus T1. And keep in mind now the ratio of the temperature is the same, so I'm going to do one more thing here. And so we actually know that T2 over T jet, so T2 over T jet is the same as T1 over T0. So this equation actually becomes 1 minus, I'm going to pull the T0 out, And so we have T jet over T0 minus 1. And then I'm going to pull the T1 out. And so this is T2 over T1 minus T1. Well, I just said that T2 over T jet, T0, T1. So those are actually the same terms. So this whole thermodynamic efficiency is actually just 1 minus T0 over T1. So it's really 1 minus the ratio of the temperatures, which is actually this term here. So this is just 1 minus 1 plus gamma minus 1 over 2 Mach 1 squared over 1 plus gamma minus 1 over 2 Mach 0 squared. All right, so that's a big one. I'm going to circle that in a different color. Okay, so what this means is that for a ramjet, unless we're adding more pressure ratio with a compressor fan, the thermal efficiency of our entire system basically is set by what's the combustion speed that's happening. And so, next video I'll show you some plots of this, because that's like really easy to do. This is as your free stream velocity changes. If I want my combustion speed to be Mach 0.5, I want it to be subsonic. Well, then this just says that actually my thermal efficiency is going to get better as I get faster, and we know that. We actually know that at slower speeds, ramjets are really horrible, propulsion systems. It's kind of Mach 3, Mach 4, Mach 5 higher. That's where they start being pretty awesome. Now, what we'll also then show next time is if my compression is getting more. So let's say I'm flying Mach 8 and I want to be a ramjet. I want to slow it down to Mach 0.5. Well, that's going to shift this curve at higher pressures. You're actually going to get to a point where, like, if this is your material limit, you can't. If you're already hotter than this, like you're done. You can't even add energy to it. So kind of forget about it. All right. And then once we have this thermal energy, we can actually come back. I'm going to come back to this equation here, because now that we solve for T2 thermal, I'm actually just going to say that this actually has a much easier form. So 2 over gamma minus 1, again, free stream Mach squared. And then this is just Q over CPT times, and let's get rid of that. It actually just multiplied by N thermal. Okay, so that's pretty easy. And then this form down here, kind of the last step is that you can actually solve for, because this is actually your criteria, you can actually you can see that the amount of heat you can put into the system is T2 over T0 minus 1 over 1 minus eta thermal. So, walk you through this again. I have an aircraft that I'm flying at some Mach number. I'm going to do a ramjet, so I'm going to slow it down to, say, Mach 0.5. And the answer is this: if this is Mach 0, it doesn't change too much. So you would set Mach 0.5. Boom! I've now got my thermal efficiency for the cycle, because that flying at this Mach number, going to ramming it down, actually sets its point. Great. Then I'm going to come to this. So that's kind of here. I'll do it in blue. So what you're doing here is step 1. Get your thermal efficiency. Now you have your thermal efficiency. Well, what's step 2? Well, I have a material limit here. I can't, I would like to add fuel, but I'm going to add fuel only up to, and combustion only up to the point where this T2 or T0 happens. Well, a good choice of this is, say 10. At high altitudes, we're talking about the air might be minus 40, minus 50, doesn't really matter. 10 times that, again, from an absolute scale, puts the temperatures at about 3,500 Fahrenheit. So that's probably kind of the material limit you would want to have within a ram combustor. And so if you set that to 10, right, I just found my thermal efficiency, I can now get how much heat I'm adding. And it's normalized by, that's the T0. So this is sort of step 2. I can solve for how much heat I'm adding in. Now that I've got that, I'm going to come back up here, and now I can solve for the jet velocity compared to the free stream. So this is now step 3. And then I didn't finish writing this form. this actually simplifies down to 2 over 1 plus v jet over v0. And so I've now got the difference from my jet to my outside velocity. So that is step 4, and we're done, right? We actually now fully understand what's going on. And then you know, if we need to then size the system, well, I'll come over here and just say that our thrust, again, put this up here, that thrust is equal to rho naught v naught. Those are conditions. I want to fly at this altitude and the speed times the area, and then if I pull out another v naught, that's actually squared, and then that's v j over v0 minus 1. I input that in there. So now I can solve for A. If I need an engine that makes, you know, when I'm adding this much fuel, if it makes this much thrust, I've got it. I'm done. I've now sized my engine. And so this is, again, just very, you know, while it's a lot of equations, it's very simplistic. The only thing we've assumed here is constant pressure, heat addition, okay? And the rest just kind of falls out. And so, you know, when we think through, ultimately, I'm going to write down here kind of the big punchline. As you go back to kind of our earlier conversations, that within the range equation, you have sort of the heating value over g times rate of propulsion. Now, that's the same thing as ISP times the velocity that you're flying at. So if you want to find ISP, well, you're done. That, again, the heating value divided by g for kerosene is, you know, 4,400 kilometers. It's a great unit. It's 12,000 for hydrogen, but we've shown how hydrogen is pretty horrible. And so if you're looking to solve for your ISP, you actually already have it. And so if you wanted to do anything else, you could just add a knockdown efficiency on top of all this. But basically, everything falls out by setting the temperature or the speed you're flying at, your maximum temperature that you're willing to accept within your ramjet system, and you're done. You actually have your full propulsion efficiency, and then you can go look at things like range and ISP, and all those things fall out of all of this. So that's what we'll do next time. We'll show you a bunch of those graphs that just kind of fall out of this, and we can really gather some really interesting things from just this basic assumption. So we'll see you next time.